Hi everyone. Today in this video we will discuss about the 6 question from the first set of mechanical engineering question paper from the GATE 2020 question paper. The question is, a single degree of freedom oscillator is subjected to a harmonic excitation f of t equal to f naught cos omega t as shown in the figure. The non-zero value of omega for which the amplitude of the force transmitted to the ground will be f naught is option A under root of k by 2m, option B root of k by m, option C whole root of 2k by m, and option D 2 into under root k by m. You can refer to the NPTEL course or video Mechanical Vibration web coordinated by IIT Guwahati. So let us move to the basic useful data. To solve this question, you should know what is transmissibility. Transmissibility is defined as the ratio between amplitude of force transmitted to the foundation and amplitude of excitation force or disturbing force. So epsilon is equal to Ft by F naught, where Ft is the transmitted force and F naught is the excitation or disturbing force. It can be derived as epsilon equal to under root of 1 plus 2 zeta r whole square divided by 1 minus r whole square into 2 zeta r whole square, where r is the frequency ratio omega by omega n, and zeta is the damping ratio. We will be explaining about all this when we are going to the video solution. As we discussed earlier, the transmissibility epsilon is defined as is a ratio of Ft by F naught, where Ft is the amplitude of the transmitted force and F naught is the excitation force. And by deriving, using derivation, we can get this transmissibility as ratio of 1 plus 2 zeta r whole square divided by under root 1 minus r square whole square plus 2 zeta r whole square. What is r? R is nothing but omega by omega n, and zeta is a damping coefficient. Okay, now using this we can plot the transmissibility versus R. Like if we wanted to make a graph between the transmissibility and R, where R is omega by omega n. So it can start from R is equal to 0, that means omega is 0, excitation force is 0, and omega can go to a higher number. Okay, so but R is equal to omega, R equal to 1 means the point comes around here. So what happens at R is equal to 1? When R is equal to 1, omega by omega n is equal to 1, omega is equal to omega n, which is a condition of resonance. Okay, this is just a point. Okay, now what happens if R is equal to 0? That means omega by omega n equal to 0, which happens at omega is equal to 0. If you substitute R is equal to 0, you will get this transmissibility as 1, because this term will go to 0 and this term will be 1 and this term is 0. So 1 by 1 you will get 1. And for large value of R, we can say that this transmissibility approaches to 0. Next, okay, now if we plot this graph for different values of damping coefficient, the graph will look like this. It reaches to a maximum around omega is equal to omega, and then it comes to this goes to 0, approaches 0. For undamped case, that means this is for zeta not equal to 0. If zeta is 0, the curve will be, if this is omega, okay, so this curve will go to infinity, and then this infinity, then from here it will go, and then it reaches to 0 fastly. And for any other values of omega, if this is for zeta is equal to 0, okay, so let us say this is zeta equal to 1. Okay, now for zeta greater than 1, let us say greater than zeta equal to 2, it will reach maximum before zeta equal to 1, and then it will pass through this point and then goes like this. And for zeta, for larger value, it goes like this. So you can notice that this point, the transmissibility is meeting, and at this point the transmissibility is 1. Okay, so what is this point? We can say, we can actually find this, because we know that transmissibility equal to 1. So we'll solve the RHS of this equation. So that will become 1 plus 2 zeta r whole square under root equal to root of 1 minus r whole square plus 2 zeta r whole square. Now taking the square on both sides, let us solve here. So 1 plus 2 zeta r whole square equal to 1 minus r whole square plus 2 zeta r whole square, and this thing will become cancel. So 1 minus r whole square equal to 1. 1 minus r whole square equal to 1 whole square. Now you take its roots. 1 minus r whole square is equal to plus or minus 1. So it can be 1 minus r is equal to 1 or 1 minus r equal to minus 1. So r here, solving this, r is equal to, taking this to this become 0. So r is equal to 0, which we said earlier that when r is equal to 0, the transmissibility will be 1 when you substitute in this equation. Next, other one is 1 minus r square is equal to minus 1. Then for r square is equal to 2, and r is equal to plus or minus 2, but r is always positive. So r is equal to, r is positive or greater than or equal to 0. Therefore r is equal to root 2. So at this point we can say that when r is equal to root 2, it crosses to this value and then increases. Like you can see from this graph, for zeta is equal to 0, it goes to infinity and then decreases, pass through this one, and then reaches to 0 quickly. Then for other higher values of damping, so for very low, for very high damping, it will reach its maximum much earlier, and then it doesn't goes to 0 quickly. It goes as like it will take some time. Okay, this is one observation that you can take. Okay, anyway, to solve this kind of questions, you should know about this graph. This graph should be in your mind. I'll repeat it again. So the transmissibility graph will be look like this. This is epsilon, which is the transmissibility, and here is the r. So the graph will reach point 1 two times. That is one at r is equal to 0 and root 2. So this is equal to, r is equal to 1, which is a resonant condition. So for undamped case, it will go like this for them. For higher zeta, like that. Okay, then that's it about this concept. And you also should know about this formula: epsilon is equal to 1 plus 2 zeta r whole square divided by 1 minus r whole square into zeta r whole square. You can remember this equation by, you can consider both on the the same equation in the numerator and denominator. In the numerator, for this equation, this r is 0. So you can remember like that. So this is a very easy question. You can solve it very easily. So now you know the question. What is the question? Is that we have to find an omega other than 0 at which the transmissibility is 1. So its question has told that it's not this, it's this. R is equal to root 2. So what is R is omega by omega n equal to root 2. Therefore omega is equal to root 2 omega n. And what is omega n? Omega n is nothing but under root of k by m, which we know. So the answer will be omega equals to root 2 into root of k by m. And if you take the root 2 inside, you will get k by m. So the answer is 2k by m under root omega, where at which transmissibility equal to 1. Okay, now let us move to the question again. This was a question: a single degree of freedom oscillator is subjected to harmonic excitation. The non-zero value of omega for which the amplitude of the force transmitted to ground will be F0. As we have discussed earlier, transmissibility will be 1 for R value equal to 0 and root 2. When R is equal to 0, the omega is 0. But the question is here asked is the non-zero value of omega. That will happen when R is equal to root 2. So if you know root 2, R is equal to root 2, then omega is nothing but root 2 into omega n. That is root 2 into under root k by m, that is 2k by m, and the answer is option C. You can further refer to the NPTEL video, Mechanical Vibration, coordinated by IIT Guwahati for more clarification. Thank you.